Welcome! In this video, we'll be solving LeetCode problem number 77, titled Combinations. This problem challenges us to generate all possible combinations of size k from a range of numbers. It's a great exercise to deepen your understanding of backtracking and explore efficient approaches to solving combinatorial problems. Let's dive in. In this problem, we are tasked with generating all possible combinations of k numbers chosen from a given range, 1 and n. The order in which these combinations are returned does not matter. To clarify the input, n represents the upper limit of the range, and k is the number of elements we need to select. Both n and k must meet the constraints. N can be any integer from 1 to 20, and k must be between 1 and n. The output is expected to be a list of lists, where each inner list contains a unique combination of k numbers. For example, if n equals 4 and k equals 2, the output will list all pairs of numbers that can be formed from the range 1, 4, such as 1, 2, 1, 3, and so on. This is the core idea we'll work with in solving the problem. Now, let's look deeper into what this means through examples. If n equals 4 and k equals 2, the output will be all the possible combinations of two numbers chosen from the range 1, 4. You can see combinations like 1, 2, 1, 3, 1, 4, and so forth, listed in any order. The order of the combinations themselves does not matter, only that every possible pair is included. Another example is when n equals 1 and k equals 1. Here, the range 1, 1 contains only one number, so the only valid combination is 1. This demonstrates that when k equals 1, the result is just the numbers themselves as individual combinations. Let's consider a slightly larger case next. For n equals 5 and k equals 3, the output is the set of all combinations of three numbers chosen from the range 1, 5. The result includes combinations such as 1, 2, 3, 1, 2, 4, 1, 2, 5, and many more, up to 3, 4, 5. Again, the order of these combinations does not matter as long as every possible group of three numbers is included. It's important to note that the constraints for this problem allow n to go up to 20. This means that as n and k grow larger, the number of combinations increases significantly. For example, if n were 20 and k were 10, the number of combinations would reach 184,756, so efficiency in your solution will be crucial. When analyzing edge cases, we can identify a few scenarios worth considering. For the smallest inputs, such as n equals 1 and k equals 1, the result is simply 1, because there's only one number to choose. If k equals n, for instance n equals 5 and k equals 5, the result is just the entire range itself, 1, 2, 3, 4, 5. For large inputs, such as n equals 20 and k equals 10, the algorithm must generate 184,756 combinations efficiently. If k equals 1, regardless of the value of n, the result will be each number in the range as an individual combination, like 1, 2, n. Although the problem guarantees that k is at least 1, it's worth noting that mathematically, if k were 0, the result would be the empty set. These edge cases help ensure that all possible scenarios are accounted for in your solution. To begin, let's consider different approaches to solving the problem of generating all combinations of size k from the range 1 and n. The most straightforward method is the brute force approach. Here, you would use nested loops, where each loop picks one number, continuing until you form a combination of size k. While this approach is intuitive, it quickly becomes impractical as n and k increase. The reason lies in the sheer number of combinations, which is given by nec, or n factorial divided by the product of k factorial and nk factorial. This value grows exponentially, making brute force computationally expensive and inefficient for larger inputs. On the other hand, the backtracking approach offers a more systematic way to explore all possible combinations. By building combinations incrementally and only proceeding when the current partial solution has the potential to lead to a valid result, we can avoid unnecessary computations. If a combination cannot lead to a solution, we simply backtrack and try other possibilities, significantly improving efficiency over brute force methods. Now, with backtracking, there are a few key principles to keep in mind. First, we ensure that combinations are built in ascending order to avoid redundant exploration, such as generating 1, 2, and 2, 1. This reduces unnecessary work. Second, at each step, we have two choices for the current number, either include it in the combination or skip it. Once the current combination's length reaches k, we add it to the result list. To implement this, we can use a recursive helper function, backtrack, start, path. Here, start represents the starting number for the current step, and path keeps track of the current combination. If the size of path equals k, we add it to our results. Otherwise, we iterate from the starting number to n, recursively call backtrack for the next step, and backtrack by removing the last number to explore other options. The time complexity here is O, k*, accounting for the combinations generated and the constant time operations performed for each. The space complexity is O, k, due to the recursion stack. While there's also an iterative approach, which uses a queue or dynamic programming-like method to extend partial combinations, it tends to be less intuitive and harder to implement compared to backtracking. Iterative methods, while avoiding recursion, introduce their own trade-offs. One key observation is that they often require additional memory to maintain intermediate states, which can make the approach less elegant. Although they might be slightly faster in specific scenarios, iterative methods are typically harder to adapt for problems involving constraints like ascending order, as seen in this problem. Given these considerations, backtracking emerges as the preferred strategy. It allows for systematic and efficient exploration of all valid combinations without redundancy. Its recursive structure inherently handles constraints, such as ensuring combinations are in ascending order, while avoiding unnecessary computations. Moreover, backtracking is intuitive and straightforward to implement, making it well-suited for problems involving subsets or combinations. These factors make it the ideal choice for solving this problem. Backtracking has its own set of trade-offs, which balance its strengths and weaknesses. On the positive side, it provides efficient exploration of valid combinations and scales well within the problem's constraints, as n is capped at 20. Additionally, the algorithm is simple to implement and debug, which is a significant advantage when working on complex problems. However, there are some downsides. Recursive calls can lead to higher memory usage, especially when k is large, and the recursion overhead may make it slightly slower than iterative approaches for small values of n. Nonetheless, the final complexity analysis reinforces its practicality. The time complexity remains O, k*, since we generate all combinations and perform constant time operations for each. The space complexity is O, k, stemming from the recursion stack. Overall, backtracking strikes the best balance between efficiency, simplicity, and practicality, making it the most suitable approach for solving this problem within the given constraints. The problem we are solving here is about generating all possible combinations of size k from a given range of numbers between 1 and n. For instance, if n equals 4 and k equals 2, the valid combinations are 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4. Our objective is to compute these combinations efficiently. To achieve this, we begin with input validation. First, if k is greater than n, we return an empty list because it's impossible to form such combinations. Similarly, if k equals 0, we return a list containing a single empty combination, as even a combination of size 0 is valid. Next, we use a recursive backtracking approach to systematically generate the combinations. The core idea is to explore each number in the range as the starting point of a combination. At each step, we append a number to the current combination, recursively explore the next numbers, and once a combination reaches size k, we add it to our result list. Backtracking ensures that we remove the recently added number to explore other paths. This systematic approach enables us to generate all combinations efficiently. Now, let's discuss the base case and optimizations for this approach. The base case occurs when the current combination size equals k. At this point, we stop further exploration, save the combination to the result list, and return. To optimize the algorithm, we implement pruning. For instance, if the remaining numbers are fewer than what is required to complete the combination, there's no point in continuing down that path. This reduces unnecessary computations. Once all valid combinations are generated, we return the result list. Recursive backtracking is particularly suited for this problem because it systematically explores all possibilities while avoiding redundant computations. Additionally, pruning significantly speeds up the process by eliminating invalid paths early. Another advantage of this approach is that the combinations are generated in lexicographical order due to the ascending order of number iteration and the rule that each subsequent number in a combination must be greater than the last. This ensures the output is naturally sorted. To implement this solution, we use two main data structures, a result list and a temporary combination list. The result list stores all the valid combinations, while the temporary combination list helps in building combinations incrementally during recursion. Now, let's analyze the complexity. The time complexity is determined by the number of combinations, c, n, k, which equals n factorial divided by k factorial times n minus k factorial. Each combination is constructed in O, k time, so the overall complexity is O, k asterisk c, n, k. For space complexity, the recursion stack depth is proportional to k because at any point, the temporary combination can have at most k elements. This gives a space complexity of O, k. Let's walk through an example to see this in action. Suppose n equals 4 and k equals 2. We start with an empty combination. First, we add the number 1 and recursively build combinations. Adding 2 gives us 1, 2, a complete combination, which is added to the result. Similarly, adding 3 forms 1, 3, and adding 4 forms 1, 4. Each of these is added to the result as they are completed. After completing combinations with 1, we backtrack by removing it and start with 2. Adding 3 forms 2, 3, and adding 4 forms 2, 4. Both are complete and added to the result. Next, we try starting with 3. Adding 4 gives 3, 4, which is also added to the result. Finally, starting with 4 alone doesn't lead to any new combinations since k equals 2 and there are no larger numbers left to pair with. At the end of this process, the output contains all valid combinations 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. This systematic approach ensures that every combination of size k is explored exactly once, yielding the desired result. The solution uses a backtracking approach to generate all possible combinations of k integers from the range 1 to n. The method combine initializes an empty list result to store the combinations and calls the helper function backtrack starting from 1 with an empty path. The backtrack function is responsible for constructing combinations recursively. It takes two parameters, start, which determines the current starting point for adding numbers, and path, which represents the current combination being built. If the length of path equals k, the combination is complete and added to the result list. The for loop iterates from the current start value to n. For each number I, it is appended to the path, and backtrack is called recursively with I plus 1 as the new starting point. This ensures that each combination respects the increasing order of elements. After the recursive call, the last element is removed, path.pop, to backtrack and explore other possibilities. This approach systematically explores all valid combinations and ensures no duplicates are generated. Once all recursive calls are complete, the result list containing all combinations is returned. The solution is efficient and concise, leveraging the power of backtracking to handle the problem's constraints effectively. Here, we begin by defining our solution class and its main method, combine. This function takes two parameters, n and k. The goal is to generate all possible combinations of k numbers chosen from the range 1 to n. To achieve this, we initialize an empty list called result to store the final combinations, and we use a helper method called backtrack to handle the recursive logic. The backtrack function is defined to take several parameters, the current starting point, the range limit n, the desired size of the combination k, a temporary list called path to build combinations, and the result list to store the completed combinations. Inside the backtrack method, we first check if the size of our path list matches k. If it does, we've built a valid combination, so we make a copy of path and add it to result. If not, we iterate through the numbers starting from start up to n. For each number, we add it to the path, recursively call backtrack with the updated starting point, and then remove the most recent number to backtrack and explore other possibilities. Finally, we close the loop and recursive calls in the backtrack method. The main method demonstrates how to use the combine function. Here, we call combine for 2 to generate all combinations of two numbers from the range 1 to 4. The result is then printed to the console. This showcases how the algorithm works step by step, leveraging recursion and backtracking to explore all possible combinations efficiently. The structure of the code ensures that we only generate valid combinations, and by removing elements from the path during backtracking, we avoid unnecessary computations. This implementation is both concise and effective for solving the combinations problem. In the problem combinations, we are tasked with generating all possible combinations of k numbers chosen from the range 1 n. This is a classic backtracking problem where we systematically explore all potential combinations while adhering to certain constraints. For example, if n equals 4 and k equals 2, we need to generate all two-number combinations from the range 1, 2, 3, 4. To solve this, we use a recursive backtracking function. Initially, our result list is empty, and we start the backtracking process with start equals 1 and an empty path. The path represents the current combination we're building. In the first call to backtrack, 1, we loop through the numbers starting from 1 up to n. For I equals 1, we add 1 to the path, making it 1, and then recursively call backtrack with the next starting point, start equals 2, and the updated path, 1. In the second call, backtrack, 2, 1, we loop through numbers from 2 to 4. Starting with I equals 2, we add 2 to the path, forming 1, 2. Since the length of path is now equal to k, we append 1, 2 to the result. After this, we backtrack by removing 2 from path, reverting it to 1. We then continue the loop with I equals 3 and I equals 4, following the same steps to generate 1, 3, and 1, 4, appending each to the result. Once we've finished processing all options starting with 1, we return to the first call and remove 1 from path, making it empty again. At this point, we proceed with I equals 2, I equals 3, and I equals 4, generating new combinations such as 2, 3, 2, 4, and 3, 4, by repeating the same process. The final output for this example is 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. Now let's look at a scenario where n equals 3 and k equals 3. Our goal is to generate all combinations of size 3 from the range 1, 2, 3. We start with an empty result list and call backtrack 1. In this initial call, we loop through numbers starting from 1. Adding 1 to the path gives 1, and we make a recursive call with start equals 2 and path equals 1. In the second call, we add 2 to the path, forming 1, 2, and recur again with start equals 3 and path equals 1, 2. In the third call, we add 3 to the path, resulting in 1, 2, 3. At this point, the length of path equals k, so we append 1, 2, 3 to the result. Afterward, we backtrack step by step, removing 3, then 2, and finally 1 from the path, bringing it back to an empty state. Once the backtracking process is complete, we find that there's only one valid combination when k equals n, which is 1, 2, 3. This is because the only way to select all three numbers from the set 1, 2, 3 is to include every element. Now, consider a simpler case where n equals 5 and k equals 1. Here, we aim to generate all combinations of size 1 from the range 1, 2, 3, 4, 5. We start with an empty result, and in the first call to backtrack 1, we loop through each number from 1 to 5. For each I, we add it to the path, making it 1, 2, and so on. Since the length of path equals k for every single number, we append each individual path to the result. After appending, we backtrack by removing the number from the path to prepare for the next iteration. The final output for the case where n equals 5 and k equals 1 is 1, 2, 3, 4, 5. This shows that when k is 1, every element in the range becomes its own combination. Through these examples, we can observe some key insights about the backtracking approach. First, the method systematically explores all possibilities by incrementally building combinations in the path and backtracking using pop to explore alternatives. Second, the start parameter ensures we avoid duplicates and generate combinations in lexicographical order. Lastly, the base case, which checks if the length of path equals k, ensures that only valid combinations are added to the result. This approach has a time complexity of O, k asterisk c, n, k, where c, n, k, is the total number of combinations, and a space complexity of O, k, for the recursion stack. These properties make backtracking a powerful and efficient tool for solving combination problems. The time complexity of the combine function is primarily influenced by the total number of combinations that need to be generated and the cost of producing each combination. To calculate this, we rely on the binomial coefficient, C, n, k, which represents the total number of ways to choose k elements from a set of n. This can be expressed mathematically as n divided by the product of k and nk. Now, for each combination, the backtrack function appends the result to the result list, and since each combination contains exactly k elements, this operation takes k time. When you multiply the number of combinations, C, n, k, by the time it takes to process each combination, the total time complexity becomes C, n, k, asterisk k. In the worst-case scenario, where k is either very small or very large, the binomial coefficient reaches its maximum value. For instance, when k is around n/2, C, n, k, approaches its peak, which is approximately 2 to the power of n. This means that, in such cases, the time complexity can grow exponentially, nearing 2 to the power of n. The space complexity of the combine function also depends on two main factors: the recursion stack and the space required to store the results. First, consider the auxiliary space used by recursive calls. The depth of recursion is at most k, as the recursion halts once the combination reaches the desired size. Each recursive call holds its own set of local variables, so the space consumed by the call stack is k. Second, we must account for the space needed to store the combinations in the result list. Since there are C, n, k combinations, and each combination contains k elements, the total space required for result storage is C, n, k, asterisk k. Therefore, the overall space complexity is dominated by this result storage, making it C, n, k, asterisk k. However, if we focus only on the recursion stack and disregard the storage, the space complexity reduces to k. When comparing this backtracking solution to a brute force approach, the difference in efficiency becomes clear. A naive method might attempt to generate all possible subsets of the n elements, there are 2 to the power of n subsets in total, and then filter out the ones of size k. This brute force strategy would lead to a time complexity of 2 to the power of n, which is highly inefficient. In contrast, the optimized backtracking approach directly generates only valid combinations, avoiding the overhead of creating and filtering unnecessary subsets. Furthermore, it prunes invalid paths early, which significantly reduces needless computation. To summarize, the time complexity of this solution is C, n, k, asterisk k, though it can approach 2 to the power of n in the worst-case scenario. The space complexity is C, n, k, asterisk k, for storing results, with an additional k for the recursion stack. Overall, this backtracking method is a substantial improvement over brute force techniques, as it systematically constructs the desired combinations without producing extraneous subsets. When working on the combinations problem, there are several common mistakes you should be aware of. First, it's easy to overlook edge cases involving k and n. For example, if k is greater than n, there are no valid combinations, so the output should be an empty list. Similarly, when k is 0 or n is 0, the result must also be an empty list, but many solutions skip these checks and proceed with unnecessary recursion or loops, leading to errors or infinite loops. Another frequent issue arises in backtracking implementations, where changes made during one recursive call, like adding an element to the current combination, aren't properly undone before the next call. This failure to backtrack correctly results in incorrect outputs or excessive memory usage. Then, there's the problem of defining a recursive function's base case. If the base case doesn't trigger when the combination size reaches k, the recursion may terminate incorrectly, leading to incomplete results. Additionally, Python-specific issues can arise, such as using mutable default arguments like path satface in recursive functions. This reuses the same list across calls, often causing unintended side effects. Finally, some beginners overcomplicate brute force solutions by introducing unnecessary nested loops or redundant checks, which makes the code harder to debug and less efficient for larger inputs. When solving combination problems in interviews, understanding backtracking is crucial. This technique allows you to explore all possible combinations systematically while pruning paths that don't lead to valid solutions. It's efficient and elegant compared to brute force approaches. Be prepared to discuss the trade-offs during interviews. For instance, while brute force methods are straightforward, they're highly inefficient, especially for larger values of n and k. A backtracking, on the other hand, optimizes the process by avoiding redundant computations, though it requires a deeper understanding of recursion. You should also be able to explain the complexity of the problem. Since the number of unique combinations is given by c, n, k, equals n slash k asterisk nk, the problem naturally has exponential complexity. While it's important to optimize your implementation, it's equally important to acknowledge this inherent limitation. Lastly, interviewers often test your awareness of edge cases, so make sure you can clearly articulate how your solution handles scenarios like k greater than n, or when k or n equals 0. Combinations are a foundational concept, and there are several related problems worth exploring. For instance, LeetCode 77 is the classic problem where you generate all k-sized combinations from the numbers 1 through n, and building on this, LeetCode 39, combination sum, introduces a twist where you generate combinations that sum to a target value, allowing repeated numbers. LeetCode 40, combination sum 2, is similar but restricts you to using each number only once. Then there's LeetCode 216, combination sum 3, which limits the numbers to the range 1 through 9 and requires the combinations to sum to a specific target. Now, when considering approaches, brute force is the simplest but least efficient. This method involves either using nested loops or generating all subsets and filtering the ones of size k. It's easy to implement but has a time complexity of 2 to the power of n, which doesn't scale well for larger inputs. A more efficient approach is backtracking, where you recursively build combinations, deciding at each step whether to include a number. This approach is much faster, with a complexity of O, C, N, K, and is the most common method for solving these types of problems. In addition to brute force and backtracking, there are other approaches to consider. One is the iterative approach, which simulates the backtracking process using a stack or queue instead of recursion. This avoids issues like recursion depth limits, but it can be harder to implement and debug because you need to manage the stack manually. Another alternative is bit masking, which is a clever way of representing combinations using binary numbers. Each bit in the binary representation corresponds to whether a number is included in the combination. While this approach is elegant and works well for small n, it becomes inefficient as n grows larger because it still requires generating and checking all possible subsets, which is exponential in nature. Each of these approaches has its own trade-offs, and choosing the right one depends on the constraints of the problem and your familiarity with the method. Great job! We've tackled LeetCode problem number 77 and explored how to generate combinations of size k using backtracking. Remember that mastering backtracking is essential for solving many combinatorial problems efficiently. Keep practicing, and don't forget to like, share, and subscribe for more problem-solving tips and tutorials. Until next time, happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!